geophysical investigations. You notice we've covered, I think, a lot of groundwork. There is one more topic after this, which we can finish next week. I give you 2 weeks for your for reading. Then you sit the cut for this part, and then you wait for the exam, unless you have anything else to you want me to discuss in detail. But so far, this is if you check the course outline versus the content, I think we have covered most of it, a good percentage so far. So we are talking about additional field testing methods. These are the SPT, the Vane Shear Test, the Penetrometer Test. I'm not sure whether Pressuremeter Test is a traditional test, but still, nonetheless, we are going to. Westlin is talking. Westlin, please mute yourself. Okay, so these are the tests we're going to talk about. I'm also going to inform you of other tests that may not be very traditional, but you need to be aware they exist. The standard penetration, excuse me, penetration test is defined or described in the BS 1377. I think my notes are a little bit out of date. We should now be talking about the zero code. But still, I think that's not good enough. We should even be talking about our own country standards. Unfortunately, so far we don't have, so we have to refer to these colonial standards, so to speak. Okay, this is a dynamic cone penetrometer used to provide information on engineering property, excuse me, of soils. Please record your attendance, the name and registration. I've seen you people combine. If it's the same person, just write the name twice. You can send as many times as the name and registration number. If one person is the one writing, just write and the other name plus the registration. Should not be a big issue. So this is the the test uses a split. Someone mic is on, or if you have a question, you shoot it. Hello. Hello. Maingi. The test uses split thick-walled sample tube with an out. Yes. Hello. With an outside. Why? Anyone else with the same problem? Hello? Anyone else with the same problem? Probably it's just some lag. This internet thing, sometimes this is the issue. I don't know anyone else saying they can't see. Please respond, because now I wouldn't know if you're not saying anything.
We can see.
Yeah, so the one who cannot see, maybe something is wrong with your internet connectivity or your equipment, or your device. Yeah, although I have to be careful saying that because when you say your device, are you using a phone? And the type could be anyway. Anyway,
My laptop, but
yeah,
I think the internet has problem.
yeah, the internet. Okay, good. So you can share with your friend. You can share with your friend. Is fine. Just make sure you register your attendance. So the split spoon sampler has a outside diameter of 51, the internal diameter of 35. It means the thickness is 51 minus 35 is how much? No, that's the diameter. So if you divide that by 2, 27.5 minus 17.5, is that 27? No, 25.5 minus 17.5, about 7. That's, is it 11 minus 5, 16? About 8 millimeters. Okay, and then the hammer is driven by as the hammer itself is 363.5 kilograms and is driven through or through a height of 760 millimeters, and there is what you call a sit-in drive of 150 millimeters. So the initial penetration has to be 150 is the sit-in drive. That means you initially have to drive the sampler through 150, and this time you are not counting the number of blows. So you start that, you drive it through 150, and then you start counting now from the initial 150. Then you count the number of blows that can cause per further penetration of 300 millimeter in steps of 75 millimeter. So for every 75 millimeter, you have to count how many blows that can cause that movement, but cumulatively up to 300 millimeters. This is what the BS says. So the number of blows that can cause 300 millimeters after the sit-in drive of 150 is recorded as N. In case 50 blows are insufficient to cause an advance of 300 millimeters, then you can record that as refusal. Refusal either means that the material is quite hard, that is rock, so it means the shear strength is very high, one thing, or maybe the place is too rocky, then it means you will destroy your equipment, and these things are expensive, so you need to protect them. So if 50 blows are insufficient to cause 300 millimeter advancement, then you record that as refusal. The core purpose of the test is to give an indication of the relative density first, of the granular deposits such as sand gravels, it is virtually impossible to obtain undisturbed samples for direct testing in the laboratory. For clay, you can obtain undisturbed samples. For sands and silt, they have no cohesion, so that's a difficult thing to do. Well, you can, with some advancement, you can apply some vacuum. You can also apply some there's some mechanisms you can use to collect the sample for testing. Now the problem when you apply vacuum, in theory, if you take it to the lab, you have to remove a sample to take to put in the test equipment. Still there are challenges, but there's some you can improvise such that you can create uh, you can improvise such that you can collect the samples. The issue is the point is it could be is more challenging. So it has been observed that the interpretation of SPT results depend on the soil type, with fine-grained sands giving the most useful results, with coarse-grained sand and silty sand given reasonable useful results. This is not to say this is not useful for clays. You need to understand the context in which we are saying this. Clays and gravel soils may yield results that are poorly representative of the true in situ conditions, but it doesn't mean that they are not useful in this test. What this means is that we just need to have better correlation with the results between the in situ and the in situ actual conditions and the in a nutshell, we need to calibrate the clay results much better. The sand soils and the silts maybe have been calibrated in a better way, and the clays and the gravels have been poorly correlated. One reason for gravel soils is because of the gravel tend to have some other boulders, and so easily you can have refusal because you are hitting a rock rather than the soil. So you can say sometimes you can record refusal, but again you need to protect the equipment. So when you hit a rock and then you think the material is strong, but you're just meeting an isolated rock. So some of these are the reasons why you can there is poor correlation. Clay is complicated because clay, the poor water pressure, clay, you remember the issues of clay minerals, montmorillonite. They're quite active, some we even have sensitive clays. You remember, if you when you load it, by the sheer fact that you're loading it, you induce it into kind of a chemical reaction, so the shear strength would change or the shear strength properties would change drastically. So for these reasons, you can see why there is poor correlation. It doesn't mean that we cannot use this test, because these tests are useful. So at the figures 1.2 1.3 shows the so this is the split spoon sampler, and this is the the SPT, and of course the 30-inch, or we could say 750 760 mm. This is the standard. So sitting drive, I don't know whether it's shown here. If you can see laser pointer, sitting drive of 150, then we count how many, 18 inches, 8 times 12, 18 times 25 divided by 4, 1800 divided by 4. I don't know why they are showing 18 inches. Okay, inches are strange. We use millimeters. So the sitting drive of 150, the next that can cause 300. 300 divided by 25 is, I think, is 12, right? 12? Yes, 12. I don't know what's the purpose of the 18 inches there. Anyway, the picture is to show you the setup of the SPT. Now this is another okay, in closer look of the sampler, of the split spoon sampler. Now this is some improvised way of so sprinkle culture, because the things like sand is difficult to obtain samples. So sprinkle culture, this helps to obtain samples in such troublesome soil. So finally, this soil sample recovered from the tube is placed in glass bottle and transported to laboratory. field test is standard deviation test. A figure 1 point. Okay, the figures I've already shown here. Okay, there are other figures. Shows the split spoon sampler. So actually, these are in reality. This is the idealized the ideal picture, but this is an actual picture from the test. In fact, uh, Timothy, he has not joined, but my Google is warning me that this person isn't signed in with a Google account. They might not be who they claim they are. Class rep, do you know anyone called Timothy? We do not want they are called imposers or conmen or fraudsters. Class rep, do you know anyone called Timothy in your class?
I know him.
Okay, well, what device is he using that my Google is warning me? Anyway, so this is an actual photo of the of the split spoon sampler and collecting samples. In academia, when you use someone else's work, it's good to acknowledge. So this is a photo from these people, I think in the US, Wisconsin, and you can see from the photo that it looks like clay. So for sand, is still quite difficult to get. This is it looks like clay with some moisture. Kiprop Peter, Kiprop Terra, please mute yourself. Kiprop, 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 please mute yourself or I will eject you from the class. Please, someone call him or I will eject him because I can't concentrate. Class. Okay, very well. Yeah, so that's the split spoon sampler, and so this is like how to get the disturbance ratio. So you will realize that to get, in fact, a disturbed sample, a sample that can be considered undisturbed is quite difficult, even though the purpose of this test is to try to characterize the in situ material as best as possible. So when the ratio is 10% or less, you can see that we can consider it undisturbed. But you can see here that based on the split spoon sampler, there is 11.5% over. So the resultant sample can be considered disturbed, even though we set out to have a sample that is not disturbed. You can see. So of course, that's another philosophical discussion we may not get into at this level. So just to show you how difficult sometimes to obtain a perfectly undisturbed sample, and then that also will get into the discussion of what is the definition of disturbed or an undisturbed sample. So well, that's a discussion beyond the scope of this class. As these samples are highly disturbed, split spoon sample generally are taken at intervals of 1.5 or 5 feet. When the material encountered in the field is sand, in particular fine sand, below the water table. Recovery of the sample by split spoon sampler may be okay. They are being modest. It is difficult. May is yeah, not maybe, it is difficult. In that case, a device such as sprinkle catcher may have to be placed inside. I already shown you. It is important to point out that several factors contribute to variation of SPT number at a given depth for similar soil profiles. Among these factors are the SPT hammer efficiency, borehole diameter, excuse me, sampling method, and the rod length. These are from work of Seed, our friend called Seed in 1985. So just to tell you, we said you measure the sitting drive 150, then you count the number of blows that you can cause a further 300 millimeter blow. But that value, it depends on these factors. The n that you have counted depends on all this efficiency, borehole diameter, so that value always will have to be corrected depending on these values, and I'll show you how to do that. So if you get an n of 5, that value needs to be processed a little bit before it is used. You cannot use it that way because there are several things that have to be corrected for. For example, the SPT hammer energy efficiency. The reason, we know that the input energy is W times height. So if the 63.5 hammer, if you convert it to kilonewtons times 760, so this is the force. But if you were to measure the actual, you put something, we go up back here. If you are to have a sensor here, a sensor on the anvil, just on the anvil, and then let the hammer hit it and measure the energy, you will notice that the energy is not the same as what we are calculating in theory. And what that shows you is that there is energy loss, of course, because of friction between the hammer and the anvil first. Some of the energy is also converted to heat because they are heating each other. Probably the friction due to air. I don't know the interaction between the air. Well, but there's some distance is very small. Okay, that's something debatable, but these are things you can think about along. As also we assume there's perfection, there's perpendicularity. Probably that is not the case. And you remember we were talking about refusal. Sometimes probably you use the equipment in a rocky area, so probably it's not oriented, it's not very perpendicular. So these are some of the things, imperfections in the equipment as well. So this lead to we don't get the energy that we need. In fact, you can see that for those who have studied, they found that the energy in fact can vary from between 30 to 90%. So in standard practice, again, now we have to look up to other jurisdictions because in our country we have not developed this very well. So in the United States they refer to 60%. So whatever the case, we have to refer the value of n we obtain has to be compared against this N60, which has been used in the United States. This was proposed also by Seed. So in addition to borehole diameter, rod length, borehole depth, we also have to, there's also what you call whether there's a presence of liner. A liner is the sampler, is the sometimes you just need to measure the n without collecting the sample. But typically you put the liner plus the the liner will help you to collect the sample. So whether we have the liner or not, that also, in fact, you can see now that also it contributes to the energy loss, because then is 63.5. The liner will weigh down the will increase friction probably, and so increase in the energy loss. So therefore n value has to be corrected. I already said this. So this NH is intuitive. Of course, the meanings have been described ahead. NH is the hammer, and B is the borehole diameter, and S is whether there's a sample or not, and R is the rod length. So I think I've already described all this, and 6 is the standard uh, penetration number corrected for field conditions. So we usually represent at N60. N60 because we said that the energy is usually between 30 to 60, 30 to 90. At 30 to 90, the average is 60. So 30 plus 90 is 120, divided by 2 is 60. That's why we refer to 60. So NH is, so N is what you have measured, what you count, and H the hammer efficiency. So hammer efficiency you will know. Of course, there are standards depending on the kind of hammer. But if somehow you are to measure you put some sensor on top of the anvil, and then you see the amount of energy delivered, then you can compare versus the WH, the weight times the height, and then you can see whether the efficiency is 70, 60, and so on and so forth. Of course, different kinds of hammers we will see have already known efficiency, and all this I think we already described. The variations are based on the recommendations. So this guy Sid did some good and gave us some tables that are useful. We see in the next table. So I've told you that several hammers have already established efficiency, so you can see this. For different countries as well, we have to go look to different jurisdictions. Like I've said, in our country we don't have. We refer mostly to the US and the STM. So these are the efficiencies for different hammers. So these are the correction values, NH, so to speak. And these are so for different variations of whether there is the sampler or not. And the diameter of the hole. So NH is 1, 1.05, 1 point. No, this is not sampler. So this is the NB, the hole diameter. So between 60 to 120, the NH you don't correct. Between if the borehole diameter is 150, you use 1.05. If it is 200, you use 1.15. Then the sampler, there is a sampler attached. One if so, this is standard. Standard means there is no sampler. When you attach a liner, you reduce a little to 0.8, and when it's a liner for dense and sand and clay. So this one you use 0.8, and then it's for loop, and you use 0.9. Of course, the rod length. Also, this, if you remember what you were saying, also this thing has something to do with, you remember we talked about the arching effect. Yes, this also has something, because you remember in theory we are saying the stress would be the unit weight times the depth, the depth z, while in fact in reality the the so this is z. In reality, the stress reaches there and remains constant. So this have to be, so So the depth at, for example, 30, if you say 10, 20, 30, the depth at 30, you can imagine the soil at that point is very under high confinement, not as in comparison to maybe a depth of 10. So these are this gives you a way to look at it. So that's for the reason why you have to do these kinds of correction. And so we also like this standard test because there are some already some good correlationships. So these are the bearing capacity factors, which I'm sure you've talked about, and Q and gamma, and the bearing the angle of shearing resistance, the angle of internal friction, and also the n value. So with the n value, you in fact with the SPT value, and if you know the angle of resistance, the internal angle of friction with the n value, you can, but now here we're talking about the corrected value, right? The corrected value, you can know the bearing capacity factor. So this is why we like this. This is also some correlation based on, so somehow when you know the corrected n value here, you can know the allowable bearing capacity based on the breadth of your so this is kind of some design, so you don't need to but these are reference, you don't need to bother yourself with a lot of calculation if you have this table. So this is a reason why we like this, and such tables make your design work very easy. So this is another calculation based on the confined compressive strength, and so this is for clays. This is for clays, and so these are some other. This is according to the Indian standard. Uh, these are corrections for the overburden stress because of the confinement. So this is how to get the correction. For the Indian standard, you only need to know the overburden stress. So this is the gamma times. Sometimes when you speak, students don't just speak. So if this is the gamma times z, this is what you are saying. This is sigma. Of course, it's better if you know the pore water pressure. Then then effective stress is this gamma times z minus the pore water, and this is what you use here to read the correction factor. Not sorry, no, that's not right. Okay, let me just use a razor. Not it's okay, let me clarify. This is what you can see here. This is the overburden, so this is what you read here, and you get the correction factor there. So this is in kilogram per centimeter squared. Okay, so and then you can use or so this is in according to the Indian standard, or you can just use this equation. So once you know the overburden in kilogram per centimeter squared or in Newton, then you use this equation to get the correction factor. So you can either read off this table or use these calculations. Okay, so unless there's a question, so that's SPT correlations. These are other. You can see that there is no universal agreement on how to correct for this. So it's a big debate. Hopefully, those values are not very different. You can try for yourself at your free time. There are some other for bars of this guy. And also there is dilatancy. Dilatancy is you should have learned this. Dilatancy is okay, I think I have some notes that can explain. Dilatancy, of course you should already know this, but just to make it clear, I think where is that? Soil formation, really? No, maybe not in this class, no. Here, I believe here. Maybe here. No. Really, not here? So, yes, no. Yes, here. So first of all, sand, but this is a characteristic of dense sand, not loose sand. So for dense sand, for dense sand, of course, when you shear something, you reduce the volume. All right. So for loose sand, this is what happens if you to draw a curve of change in volume. You compress and they reach what is called the critical volume, and that's it. So that's the critical volume. So this is for loose sand. For dense sand, something strange happens. It reduces and volume is fine, reaches the critical value, and the volume again starts to increase. So that is what is called dilatancy. The reason for that is dilatancy. To better understand this is the same idea like if you try to shear, these particles get too close for comfort until they start kind of to repel each other. All right. Okay, that's in layman's term. Now, the actual reason why this happens is shown here. Of course, this is also a debate. This is also a debate, but the most cogent reason why people think this happens is this. You can see when you are shearing this volume. See, you can see this volume here and that volume is not a lot, but when this is when you are shearing and before the rolling happens. Now, when the particles get too close to each other, you can see here now you're just rolling each other this way and this way. Now when they start to roll over each other, that rolling action increases the sphericity, because they will get into contact with at some through points, certain points, and then the rolling action increases the space between the two or neighboring particles, and you can see now this volume even visually looks bigger than these two volumes combined. So that's the reason why people think this kind of behavior happens. But please note, this is only for dense sand. For clay, for for loose sand, I think I've already explained. So that's that with the dilatant behavior. So because of that, we need to correct here as well. So that's the reason why you have to correct for dilatancy. And so this is how to correct for dilatancy, and only when n is greater than 15, and also when we're talking about saturated conditions. Okay, this is according to the Indian standard, and this is according to Bazara. In Bazara, the same guy here gives us correction for dilatancy. You need to be aware because different jurisdictions have come up with their own formula. You can see they're of the same form. In fact, if we had Kenyan, probably the formula could be in the same breath. So this is the same ideas presented, but this is by Tezagi. So you can see this idea by Tezagi is more or less the one presented in the Indian standard. Most likely they are using what was presented by Tezagi. So this is a explanation according to the Indian standard why we have to correct for energy. So this is just to reinforce the same idea that we have talked about. And here now we an assignment for you to practice. So these are the depths, these are the N60 values, and this is the correction. This is how to get the correction factor. So you can correct these values. I don't know the N, then 60 values for the you can correct these values based on this formula. So in fact it appears, you can see now there you can also correct for the atmospheric pressure condition. You can see that as also you can, so if this is a saturated layer, so the first one you can use, you can assume the saturated layer is already described there. Now for the second one you can calculate assuming we don't have the saturated layer. That's an assignment for your own practice. Is unless there's a question, class rep, unless there's a question, please make sure you have registered your attendance. Unless there's a question, okay, in silence maybe means there's no question. So we move on to the Vane Shear Test. The undrained shear strength of soft clays can be determined in laboratory by a Vane Shear Test. The test can also be conducted in the field on the at the bottom of the hole. The field test can be performed even without drilling a hole by direct penetration of the Vane shear from the ground if it is provided with a strong shoe to protect it. This is a quick test which actually you put the Vane shear, apply a torque, and based on the rotation, the speed, the resistance of the soil, you can easily tell what the undrained shear strength is. Of course, there are some rules governing the way this has to be done. Like the torque has to be applied within certain range of values. Okay, so this is the Vane Shear test. Typically, the ratio of this is the most common and the most simplistic. Usually H usually the diameter equals H over 2. Okay, so into some basic maths, how to relate the strength to the shear, how to relate the torque to the shear strength. I think is simple. So this is according to the Indian standard, but it's a standard test, so it doesn't matter which standard we are referring to. The height of the vane should be equal to twice the overall diameter. We said this. Well, this is the traditional way. Otherwise, these days it doesn't matter. Well, should be at least. Of course, that ratio. There are certain vane shear. We'll see that do not necessarily fit in. Do not obey that ratio. So the diameter of the rod, of the length of the rod, are recommended at 2.6 and 60 millimeter respectively. So for conducting the test in the laboratory, a specimen of size 38 by 75, 38 by diameter. So you can see here the ratio 1 to 2 for a sample in excuse me, if you are talking about a sample in the laboratory. So class, the 507. This is attendance on 31st. Okay, so we have recorded the attendance, and so in the laboratory, this is the size of the specimen, which is fixed on a secure base to. So because the torque is applied at a certain rate, the specimen has to be secured properly. So this is why we say so, which is fixed securely at the base. The vane is gradually lowered into the specimen till the top of the vane is at a depth. Yeah, so you can see, so this is the surface, and then the entire vane shear has to be completely submerged into the soil. So until the top of the vane is about 10. So this has to be 10 to 20 millimeter below the top of the specimen. The readings of the strain indicator and torque indicator in the apparatus are noted. Okay, so torque is applied gradually to the upper and the upper end of the rod, at the rate of 6 per minute, 6 6 revolutions per minute, or this is equivalent to 0.1 degree per second. So these rules have to be obeyed, because you should remember from your mechanics of structures, the strain rate because if you apply sometimes there is not sometimes in fact the strength of a material may also depend on the strain rate. Actually, strain rate does not affect the because there's the strength is independent of anything else, is the material behavior. But the test, the way we test matters also. So the strain rate, the speed at which you rate the material, load the material, also determines this. You can get what is called an apparent reading of the strength, which is not correct. So in fact, in theory, high strain rate will give you a false high strength. So that's why you need to control. Although there is a strain rate within which, if you apply, you get the correct strength. But if you use an unreasonably high strain rate or high loading rate, you will get an unreasonably high strength as well. So this is why we have to give these restrictions. The torque acting on the specimen is indicated by a pointer fixed to the spring. So the equipment has some pointer, some way to tell you what the torque is. The shear strength of the soil is determined from the formula, which we are going to derive now. Derivation. Okay, now okay, let me go back here. Is a simple formula really, because the first of all, we contribute this. The strength is contributed to the circular by the circular section and the circular section on top there. Also the part the cylindrical part. When this thing is rotating, it will form a cylindrical failure surface, which if you view, you can view like this, where this is pi d, and this is a d. No, that is not d, this is h. So the torque torque is just force times the lever arm, right? The force times the lever arm. I don't know how to say the lever arm. Let's say lever arm, LA. Let's concentrate on how to get the force. The force would be the shear strength, which is Cu, times, see, the stress times the area, basically. So so just a minute. So the stress here is represented by the Cu, the undrained shear strength. Sorry, the undrained shear strength. So but anyway, that's the stress. Now we need to so this is the area would be pi D times H. Of course, this is the area times the stress is Cu times the lever arm is D over 2, or the radius if so wish. So the contribution due to the cylindrical part, I think, is very quite straightforward. Pi D squared H over 2, of course, times Cu. Should be fairly simple and straightforward. So that's the contribution due to the horizontal part. So that's for the cylindrical part. For the cylindrical part, I mean not the cylindrical part, sorry, for the top and the bottom, I need you to figure out. So if we have a face like this, just imagine some random area there. So we open this small strip. If you open that small strip, the thickness is dr, is so small such that, so if the radius here and the radius there is almost the same, that means this strip is small, dr is very small, so that we can say this is 2 pi r in fact, or pi d if you like, and this is also 2 pi r in theory. So the area of that strip will be 2 pi r dr. Of course, the force is times Cu. To convert it to force, torque you multiply by the radius, so 2 pi r squared. Of course, there are two of them, 2, and you integrate from 0 to d over 2. You should not see why that is difficult, because there are two of them, the top and the bottom. So that's just the the basis. So you have to add the top for the top and the bottom. I think I've already explained this. For the cylindrical part, I think I've already. So here, in this case, we're saying Cu is the same as S. I think this all the same thing that I was saying. And the integration part, two of them, 0 to d over 2. This is Cu in my presentation, so 2 pi r dr. You can't see. I think it's very easy. Very easy integration. 4 over 3 pi r cubed, 0 to d over 2. If you substitute, there's no reason why you can't see this. So okay, let me be magnanimous. 4 over 3 pi, those are all constant. Okay, pi, if we put d, that would be d cubed over 2 times 2 times 2. This one cancels that, and then 3 times 2. I mean, it's very easy. You should not have any trouble seeing where this see. Excuse me, I'm so excuse me. I mean, you cannot have any, should not have any trouble seeing why this is that. And so you can add the two. So this covers T2, T1 you already know, so you cannot see why this. And if D is h over 2, h over 2, and this simplifies to a nice I hope I have it somewhere. This simplifies to a nice, yes, simplifies to this. So there's no reason. I mean, it's a simple calculation, really. So because I'm here, I have to say this. So this one, for tapad, for the one we are talking about, it's a simple. Okay, there's a photo here. Yeah, you can see the veins are straight and straightforward. Now the veins can be tapered. For tapered, it's a little more complicated. So this is how to get the K. The K. So we were saying the torque is the same as Cu times K. Okay. So but K is this, and if we substitute this as we're saying D is H over 2. So if we substitute this as 2D, then this is what you get as K. So for the tapered edges, where these are different values, the different angles, then this is what the K is. Of course, we concentrate on the simple one. For this, you need to be aware in case, as an engineer, you find yourself when you're using that, then you can apply the adjustments as necessary. So this is the equation. This is an addition. You're simply adding the two. So for example, this is the ratio. That's what you can get at your torque. And the derived equation above is modified if the top bottom. So if for example the Vane shear is not completely submerged into the soil, so this is H1. For some reason this might happen, then this is the correction you have to apply. Okay, so you have to make some correction if the Vane shear is not completely submerged into the material. Okay. So the shear strength of the soil sample under undrained cohesions equal to the apparent cohesion Cu. Of course, this is based on some other theory that if you of course the experiment takes a very short time, and when the Vane shear rotates, even when there is a undrained condition, the time is too short. So it means the soil is not given enough chance to react. The excess pore water cannot flow away very easily, so that we can assume reasonably that this is an undrained condition. Now the Vane shear test is also used to determine the sensitivity of samples. Sensitivity is we will describe later there, but I told you sensitivity clays are very sensitive. Some of them are sensitive. By applying a load, that induces for example a chemical reaction with water, some chemical reaction sort of, and then the shear strength changes rapidly. So when you are rotating the Vane shear inside when doing the test, that can be assumed to be the remolded shear strength, right? So the test is then repeated on remolded soils. So okay, after initial test to determine the undrained shear strength of the soil, The Vane test is then rotated rapidly through revolutions to make the sample remolded. The test is then repeated on the remolded samples and the shear strength and then is repeated in remolded soils, and the shear strength is remolded, and subsequently sensitivity is the strength of undisturbed over the strength of remolded shear strength. So basically you are comparing a strength of two states. One, the strength that has not been disturbed. That means the first time you put the equipment, the Vane Shear Test equipment, inside the soil that has not been disturbed. So the first time, maybe the first time, then you record what is called undisturbed strength. Then you can rotate several times. That in the process of the Vane Shear Test rotating, it is disturbing the soil. And after you do that several times, you take again the strength. That would be the remolded shear strength. You compare the two. That is what is called sensitivity. Now, for depending on how sensitive the soil is, you can find the strength is reducing even up to a quarter of the strength, and this is due to varied reasons. So the advantages: the test is quick and simple. Number two, the Vane Shear test is mainly suited for in situ and drain shear strength in unfissured, fully saturated clay. So if for example there is a fissure that will lead to a rapid dissipation of excess pore water pressure, and then the result given there may not be very accurate, may not reflect the reality. Number three, Vane Shear test can be used to determine the sensitivity of soil conveniently. I think I've already explained this. The disadvantage is that the main disadvantage is it cannot be conducted in fissured clay. Number two, it will not give accurate results when the failure envelope is not horizontal. So, okay, these are the I think I've already explained this, no need. And so these are standard values from the US. These are standard ratios of the depth or the height in inches or in millimeters. I think I've already explained this. Field Vane Shear tests are moderately rapid and economical and are used extensively in field exploration programs. The test gives good reasonable results. Gives good reasonable results in soft and medium stiff clays and gives excellent results in determining the properties of sensitive clays. Field vane shear tests are commonly used to measure both peak and residual and drain shear strength by noting the torque required to overcome the maximum resistance, and later the torque required to rotate the vane 5 to 10 revolutions within the clay. Source of significant error in the field vane shear test are poor calibration of torque measurement and damaged vanes here. So yeah, because the torque, it uses like some second degree correlation to get the torque. You cannot imagine that it's measuring torque directly. Of course, the torque use some scale, so maybe the calibration process some scale to show, okay, maybe 1 unit shows a certain amount of torque. So if that is not done accurately, that is a source of error. Again, these vanes are put to rotate inside some material. And then these vanes should remain as perpendicular as possible. For some reason, if they are used for a long time, as inevitable as it may happen, those vanes may twist, may change orientation. So again, that would cause some errors. So what it means that the material, I mean the equipment, needs to be calibrated and also needs to be checked before used, how clean, the perpendicularity of the blades as well. Other errors may be introduced if the rate of rotation, I think I already said this, if the rate of rotation is not controlled. For actual design purposes, the Vane shear strength values obtained from the field are too high, and it is recommended that corrected. In fact, yes, this is true, because even so the rate of rotation is still very high. So like I said, if the shear strain, if the strain is high, the apparent strength you get is high, which does not reflect the reality. So in which case, so there are some people who have given us values of how to correct. There is also no universal agreement. There are several different people have used different values to tell us how to correct, of course based on the plastic index or the liquid limit. These are just formulas, and because these are several of them, if required, if for some reason you are required to use this in an exam, you will be told exactly which formula to use. Of course, all these are based on liquid limit, which the all these factors you should know, the consolidation stress and OCR values. But this is just for information sake. So these are other correction values for different researchers as well. So this is how to get this value better here. The pre-consolidation stress, this value here, uh, this value is obtained if you know what is called one-dimensional test. You put a sample, you put uh, inside some dish, and you put on top and bottom. I don't know why I'm doing this. I think there should be there should be some notes that can bring clarity onto the 1D consolidation test, I believe is here. Yeah, so basically 1D consolidation test is this. The test is done under water, under saturated conditions. The 1D, because the soil can only deform in one dimension, only the height can change. These porous stones, the if you can correct, if you can get the changes in height, which you can relate to the changes in porosity, in sorry, not porosity, in the void ratio. So you draw a curve of sigma prime and delta E. Usually the curve is a nice curve, like this. Now if you draw, sorry, Usually the curve is a nice curve like this, delta E. Now if you draw, no, this should be, if you draw tangents there, then this is the pre-consolidation stress we are talking about. See, this is delta E. Now that pre-consolidation stress stands for, means that this is the highest load this material has ever carried on in its life. I think that's the simplest I can put it. The highest stress it has ever carried, that clay has ever carried in its lifetime, and it's important. So you should have known that anyway, either way. So that's just to clarify what the pre-consolidation stress is. So from the 1D consolidate, I think this is what. So if you draw, yeah, here, if you draw a tangent to this part of the curve, and there, what you read there is the pre-consolidation stress. Okay, that's the simplest I can put it. So that's what the pre-consolidations. That's what pre-consolidation stress is. So these are different ways to calculate the beta. So that's enough with the Vane Shear test. Then we have the cone penetration test, the CPT. Now this has been this was discovered by the Dutch people. Of course, this has been implemented with computers. The initial one was could only just measure the basic the penetration and the resistance, but these days they can also measure even the pore water pressure. So this is described in the STM adopted in 1974. A small cone is attached to a rod pushed steadily through the ground at a rate of 20.32 millimeters per second. The device is attached to a vehicle that gives it a much needed large jerking force required in testing. I think I'll show you a photo. The 60-degree apex angle cone has a base of 2032 millimeters squared with a diameter of 35.56 millimeter and a height of 30.48 millimeter. The cone is attached to a sleeve of an approximate diameter 35.6 millimeter as shown. Of course, there is a figure shown below. The CPT is then driven to the ground steadily and has been used to characterize soil up to 30 meters below the soil surface. The tip of the cone measures tip resistance using strain gauges, while the sleeve has instruments that measures the sleeve friction. These parameters may be used to obtain the profile of variation of the soil type. Something is wrong. And strength, soil type and strength. So let's see. Soil type and strength. And strength with depth, an improvement over the CPT. I think I've said this led to new CPT called piezo cone penetration test, whose operation has been outlined. Now PCPT combines both electronic friction cone and piezometric cone. Piezo of course tells you that you can also measure the pore water. PCP introduces a computerized log of the tip, and resistance induces pore water pressure just behind the cone. So this is quite advanced. You may not need any human input with the PCPT. Pore pressure ratio change in pore water pressure divided by the measured pore water pressure and the lithologic interpretation of each 2 centimeter interval of subsoil. The data acquisition system include portable computer, analog, digital converter storage, hard drive or floppy drives, and strip chart convert recorder or printer printed out. So this is a pretty advanced. Actually, this can be used even to, because normally in the soil layer is some thin layers of, if for example you have 10 meter of clay and hard clay for example, or stiff clay, then you go another 20 meters of uh, of soft clay. If for some reason there's a thin layer of sand, thin lens, we call them lenses, it's typically very difficult it's typically very difficult to uh, Lydia, please mute yourself. It's typically very difficult uh, to detect if you don't have an advanced system. So the PCPT is quite advanced. You are able, can identify or recognize such thin lenses. The results of PCPT may be used for delineating soil strata, for evaluating geotechnical parameters of subsurface. Thin seams of, I think I already said this, can easily be detected due to exceptional resolution, especially though the pore water pressure channel through the, especially I think through the pore water pressure channel, uh, especially especially through the pore water pressure channel. This facet is crucial since it may be used for slope stability calculations. Considerable efforts have been made in deriving the soil engineering data from cone and piezocone data using empirical statistical studies, numerical simulations, analytical studies, statistical analysis, and back analysis methodologies have been developed. So Mayan 1995 report that many development in the CPT have centered on its use for geoenvironmental concerns. The incorporation of additional sensors within the penetrometer to instantaneously and continuously monitor phenomena offers significant potential for evaluating subsurface chemical and biological conditions. To illustrate the foregoing argument, the current data may be used to detect if pore water is contaminated. So this is very advanced. We can even tell whether pore water is pure water or not. In addition, modifications and add-on modules to the SPT, the standard current penetrometer, such as direct push technology, has led to other specialized probe for sampling and testing groundwater and soil during environmental site characterizations, including push-in water samplers, push-in piezometer, and soil gas extraction type samples. So it's quite advanced that you can even tell the whether water is contaminated or not. A specialized device called hydrotap is commercially available. Made groundwater sampler used to obtain volatile organic compounds under controlled confining pressure conditions. CPT data are routinely used for analysis and design of foundations, including bearing capacity and settlement of spread footings, driven shaft, board piles, driven piles. Both direct and indirect CPT assessments may be used. The CPT is useful in assessing compaction level, during placement of structural fields and the evaluation of ground modification. Techniques such as vibrocompression and vibroflotation and site improvement. So sometimes, for example, if you guys remember or have heard about the the reclaimed island in Dubai is called what, the Pine. Is it the Pine Island? Is that the correct name? There's a land. There's an artificially made island in Dubai. Those who like football, I hear Ronaldo has a hotel, has bought a hotel there. The Sometimes when you're doing construction underwater, you need to check the quality. Sometimes it's very difficult. So the PCPT is quite developed in that sense. So this is the vehicle that is supposed to give the reaction to the driving force. So this is the tip, and then there's a sleeve. They have some sensors that can measure. So this is the actual photo you can see on the right. The friction ratio defined as the sleeve friction and the cone resistance. The This is an actual photo of what is happening. You can see there, and on the right is a typical. This is for the sleeve, and no, this is the cone penetration, cone resistance, and this is the sleeve resistance, and you can see the profile. And this can be obtained within matters of minutes from this advanced test. Of course, the initial one was just very rudimentary, but of course with time there is improvement. Of course, we like also these curves that based on this test we can tell so much. Where, for example, the relative density. Of course, you can see this the sleeve and the cone resistance penetration is related to the relative density. We also like the fact that based on the friction ratio, of course, the result of the cone penetration test, we can tell whether the soil is silty, gray, gravel, and so on. So this depends on how well also this system is calibrated. But just to demonstrate the usage, so we have several SPT, CPT calibration, because these are very traditional tests. So in term, if for example you have CPT results, then you can convert to SPT, or if you have SPT results, you can convert to CPT. Is quite useful for us. In any case, you have seen that if you have the SPT results, things that usually disturb people, like the bearing capacity, there are tables already, so this is useful. It's what you need to know. Of course, we have this is a relatively new. It's not new actually. It's not very new, but relatively new. This was done by this was in fact discovered by agriculturalists, and this is the second thing civil engineers have stolen or have borrowed from agriculturalist engineers. The first thing you guys borrowed. Anyone with an idea? I don't know whether it's the only. There's another thing you borrowed. Anyone who knows? Class rep? Class rep? Anyone who knows anything you borrowed? Hello? Hello? Anyone? Mr. Victor Nyakundi. Hello?
Hello.
Do you have any idea?
I don't have an idea.
So the first thing you borrowed was the Casagrande tool. They wanted to get some to measure the PI. They didn't call it PI for them. They of course they were also doing something related to the water content for the agricultural production. Now this the same thing. These people wanted to know because of leaching. If soil, if water drops, then soluble materials, dissolved salts are soluble materials are dissolved, then are deposited somewhere here, especially if we have calcium. Then calcium has cementing properties and they form what is called a hard pan. And here this is very problematic for agriculturalists. And if you're plowing or doing agriculture, you must make sure that when you're plowing, you break the hard pan because it's a problem. So they used this equipment to tell where the hard pan is. Of course, has something to do with the resistance. Now, the highway people decided now they can use this to test the resistance. You can see this guy using on a highway. The resistance of the pavement, there is a pavement basically. To control the quality of the pavement, of course, is based on the resistance as well. And eventually, geotechnical engineers or foundation people think that because it's measuring resistance, then we can also use it to measure somehow tell the quality of the foundation soils. So here the hammer is 8 kilogram and it drops through 575. The 575. Please note the difference between this and the CPT as well. But this is quite portable. CPT 63 kilogram. I think is quite difficult to carry. This is quite portable. And of course, again, the same. You drop the hammer through that height, and then you see how much the tip is able to advance. The same limitations of CPT. Again, you have to check if there's boulder that can destroy the equipment. Oh, this one is relatively portable. Actually, you can carry. Of course, these are some correlationships, but you can see they have a lot of highway people because this is they are the people who adopted it first. So there's some CBR relationship between the CBR and the penetration. These are some results and their sources just to show you the origin. So this is something briefly about the dynamic cone penetrometer test. Then we have the Pressuremeter test. Maybe we take a break for 10 minutes and then we resume. So we resume at 3:05. So we move on. So we also have this is called Pressuremeter test. Is an in-situ test conducted in borehole. It was originally developed by this guy in 1956 to measure the strength and deformability of the soil. It has been adopted by STM. So, as adopted as by this STM. The Maynard type PMT consists of essentially a probe with 3 cells. Just a minute. So the the top and bottom ones are guard cells. The middle one is a measuring cell as shown. I think there's a diagram we're gonna see shortly. The test is conducted in a pre-bored hole and diameter that is between 1.3 and 1.2 times the nominal diameter of the probe. That is commonly used and has a diameter of 58 and a length of 420. The probe cells can be expanded by either liquid or gas. The guard cells are expanded to reduce the end condition. The effect of the cell, which has V naught of 535, following the dimensions of the probe diameter and the diameter of the ball as recommended. So if you use this kind of diameter, this is the nominal diameter, and the maximum that you can use, diameter that you can use. So this is the guard cell, and this is the cell. So basically, you can apply water or gas to fill these cells, and then you have a curve as shown on the right side. So these are this is the curve, and these are so based on the changes in volume, and then somehow you can say something about the strength of the soil. So in order to conduct the test, measuring cell volume V naught is measured, and the probe is inserted into the borehole. Pressure is applied in increments, and the new volume of the cell is measured. The process is continued until soil fails. The or until the pressure limit of the device is reached. The soil is considered to have failed when the total volume of expanded cavity is about twice the volume of the original cavity. Upon completion of the test, the probe is deflated and advanced for testing at another depth. So this can be done at different depth. If for now the test is at this depth, so if you needed to do this same test in another depth, you can deflate and then continue, increase, or even use go to a shallower height if you wish. So the graphical representation I've already shown you, and it represents the reloading portion. So what we are trying to do is basically because when you create the hole, you are unloading. So there's a space here, so it means the soil which is under pressure wants to flow inside this place that is empty. So what you are doing when you are pumping the gas or the air, you're simply trying to restore the strength. I mean to balance out the pressure that was initially there. So I think the principle is very simple. To the point that this soil fails, it means that the strength, you have restored the stress condition back to exactly what it was before the point of imminent failure. So represents the reloading portion during which the soil Around the borehole is pushed back to the initial state before drilling. The pressure P naught represents the in situ total horizontal stress, as 1,2 represents the elastic zone. The cell volume versus the cell pressure is practically linear. The PF represents the creep or the yield pressure. The zone marked 3 is the plastic zone. The pressure P1 represents the limit pressure. Figure 1.7 shows pressure test in the field. And the pressure modulus EP of the soil determined using theory of expansion of the cylinder as shown. So these are based on theory of course, theory of elasticity and theory of expansion and contraction. So based on that, we can get the Young's modulus. The Poisson's ratio is fairly can be assumed to be this value, and these are values from the pressuremeter test. The limit pressure P1 is usually obtained by extrapolation and not by direct measurement. In order to overcome the difficulty of preparing the borehole to proper size, self-bore pressuremeter have also been developed. Detailed information can be found uh, in this work. So this is a pressuremeter test in reality, in actuality. So correlation between various soil parameters and the results obtained from pressuremeter tests have been developed by various researchers, as you can see. So this is the limiting pressure has been correlated also to the overburden pressure, as you can see. No, sorry, not overburden, but the pre-consolidation pressure. I think you remember the pre-consolidation. I think I've tried to explain this pre-consolidation stress. This one, where you read off your sigma C from there. So this also has been uh, so we can also relate the undrained shear strength based on the PL and P naught, and these are the definition of the definitions of the symbols you used. So typical values of NP vary between 5 and 12 with an average of 8.5 for these researchers. So these are different EP obtained from the test. Remember the S60. So these are crucial values. So for clay, for sand, and these are other tests. In fact, here we were talking about the traditional test, but in fact there are other tests. So this dilatometer test, you need to be aware. We have the our ball test, shear test, K-naught test. All these try to give you different ways to estimate the shear strength of the soil. Yes, so in addition to the traditional test, but for the purposes of this topic, you need to know about the CPT, the SPT, the dynamic cone penetrometer test. I'm not very much sure about the pressuremeter test. The pressuremeter test is useful, but is not very traditional. So the also the traditional one is the Vane Shear test. The rest you need to be aware because you need to know what happens outside the field. So this is why I mentioned these values. Just a minute. Just a minute, wait.